Every single thing AI does, writing text, generating images, driving a car, it all comes down to one idea. Take some input and map it to the right output. That's it. That's the whole field. It's called function approximation. The rest of this video is just how do we build a function like that and get it to learn the mapping on its own. Let's start with the smallest possible building block. Before a neural network can process anything, it first turns it into numbers. A word, a pixel, a sound. Each one becomes a list of numbers called a vector. Plot those vectors in space, and something remarkable happens. Things that mean similar things end up near each other. This is called an embedding space, and it's the coordinate system AI thinks in. All of those vectors get combined using one operation over and over, matrix multiplication. A CPU does this one calculation at a time. A GPU does thousands at once. That's the entire reason AI exploded in the last decade. Hardware built to render video game pixels turned out to be perfect for this math. Let's look at how AI actually works, starting with a single artificial neuron. It takes in a set of inputs. Each one gets multiplied by a weight, a number that reflects how important it is. Those weighted inputs are combined inside the neuron, producing a single output. Watch the signal actually flow. Each input travels along its weighted connection into the neuron, and the combined result flows out as the output. Mathematically, that's just y equals the activation of the weighted sum of the inputs plus a bias. Chapter 3. The learnable function. So how does a network actually learn its weights? Run the input forward, see what it predicts, and measure how wrong that prediction was. That's the loss. Then work backward. Figure out exactly how much each individual weight contributed to that error. That's backpropagation. Nudge every weight a tiny bit in the direction that reduces the error, and repeat this millions of times. That's gradient descent, and the error just keeps shrinking. But a model that just memorizes its training data isn't actually intelligent. It's a lookup table. If it memorizes too hard, it fails the moment it sees something new. That's called overfitting. The real goal is generalization, performing well on data it's never seen before. Modern AI fights this with tricks like dropout, randomly switching off parts of the network during training, so it can't just memorize. Now let's zoom into language specifically. When you type a sentence, the model doesn't read whole words. It breaks text into pieces called tokens, sometimes splitting a single word in unexpected places. Each token becomes one of those numeric IDs from a fixed vocabulary. And there's a limit to how many tokens the model can look at once. That's called the context window. In 2017, one architecture changed everything: the transformer. Its key trick is called self-attention. Every token looks at every other token and decides how much to pay attention to each one. The word it can look back at on cat and realize that's what it's actually referring to. Every token asks a query, compares it against every other token's key, and pulls in that token's value based on how well they match. Stack this mechanism dozens of layers deep, and you get a model that understands context remarkably well. But attention has a cost. Every token compares to every other token, so doubling your text roughly quadruples the compute. A newer family of architectures, like Mamba, process tokens one at a time in a rolling summary instead, scaling linearly rather than quadratically. So, how does a trained model actually generate text? One token at a time. Given everything so far, it computes a probability for every possible next token. The cat sat on there might give 70% to matte, 10% to floor, and tiny slivers to everything else. Sampling strategies, though, like temperature and top P, decide how much randomness to allow when picking from that distribution. Generating one token at a time sounds slow, and it would be if the model recomputed everything from scratch each time. Instead, it caches the keys and values from every previous token, so each new token only does a small amount of new work. That's the KV cache. Models are also compressed, quantized, from 16-bit numbers down to 4-bit, shrinking their memory footprint massively with barely any quality loss. Here's the strange empirical fact driving the entire industry. Performance improves in a remarkably predictable way as you scale up compute, data, and parameters. Research from Kaplan and Chinchilla even found an optimal ratio between how big your model should be and how much data you train it on. This is why companies spend billions on bigger training runs. The scaling curve keeps paying off. Before generative AI, computer vision was solved with a different architecture, the convolutional neural network. It slides small filters across the image, first detecting simple edges, then combining those into shapes, then whole objects. Each layer builds on the last, going from raw pixels to genuine understanding of what's in the image. Modern image generators work completely differently. They don't paint an image, they sculpt it out of noise. Start with pure random static, and a neural network predicts, step by step, what noise to remove. Do this dozens of times, guided by your text prompt, and a coherent image gradually emerges from the chaos. This process is called diffusion, and it's the technology behind Midjourney, Dolly, and Stable Diffusion. Video generation takes the same diffusion idea and adds a new dimension, time. Instead of denoising a single image, the model denoises an entire sequence of frames together, so objects stay consistent as they move. That consistency is what lets these models act as early simulators of the physical world. Getting a model from raw internet text to a helpful assistant happens in stages. First, pre-training. The model reads a huge slice of the internet, just learning to predict the next token. Then, supervised fine-tuning. It's shown curated examples of good question and answer behavior. Finally, reinforcement learning from human feedback. Humans rank different responses, and the model is nudged to produce more of what people actually prefer. Human feedback doesn't scale forever, so labs increasingly train on data generated by other AI models instead. And a newer technique called DPO skips the reinforcement learning loop entirely, directly optimizing the model to prefer better responses over worse ones. You can actually do a small version of this yourself on a single consumer GPU. Take an open source base model and fine-tune it using a technique called LoRa, which only trains a small set of new parameters instead of the whole model. Tools like Hugging Faces libraries make this a few dozen lines of code. These models don't actually know what's true. They're optimizing for what sounds plausible. That's why they sometimes confidently make things up entirely. We call this hallucination. And even the researchers who build these models can't fully explain why any single output came out the way it did. It's a black box we're still learning to read. One practical fix for hallucination: don't rely purely on what the model memorized. Instead, search a database of real documents for relevant facts and hand those to the model alongside the question. This is called retrieval-augmented generation, and it grounds the model's answer in actual retrieved evidence. Everything we've covered, text, images, video, is converging into single models that handle all of it at once. The next frontier is agents, models that don't just answer, but plan, use tools, and take actions on their own. Whether this path leads all the way to artificial general intelligence is still genuinely unknown, but the trajectory so far keeps climbing.